So when we try solving these quadratic inequalities, the goal is let's push all the terms onto one side of the inequality, right? Because then what that allows us to do is find a way to factor, right? We can factor and then use our zero product property, look for those critical points, create a number line, split it up, and then we test, right? We test to see where the solutions would make true statements. And then wherever we have true statements, that's the interval where the solutions exist. So first step is let's bring all the terms over to one side. We can do that by subtracting x from both sides and also by subtracting 2 from both sides. Here, these will cancel. So what we're left with is x squared minus x minus 2 greater than 0. All right. So now in this case, what we can do is factor the expression on the left side. And we can see, all right, in order to get x squared, that factors into x times x. We want a product or a pair of numbers that will multiply to be negative 2, but add up to be negative 1. So those factors would have to be anybody. What you got? Negative 2 and positive 1. Right. I think that would be okay. That would look good. So what does this help us do? This helps us then find those critical points or those boundary points because we can then split it up. Right, using zero product property. So what we need here is that x will be equal to 2, and here x will be equal to negative 1. So we can create a number line. And on this number line, we have negative 1 and 2. So let's see if you guys remember. On negative 1 and 2, would we have open circles or closed circles? And how would you know? Right, open, because we're following what the inequality gives us, right? So if the inequality is only greater than, right, but not equal to, then that means we cannot include these boundary points. So these are open circles. All right, and so now we need to test. We need to test each one of these intervals. So we basically have like interval A, interval B, interval C. So we can pick a point on this side of negative 1. We could pick negative 2, and then we test it. And where do we test it? We go back and we test it with the inequality where we have factored terms. Okay, so we'll test it as negative 2 minus 2 times negative 2 plus 1. And we're testing to see if that's greater than 0. So negative 2 minus 2 is negative 4, and negative 2 plus 1 is still negative 1. So negative times negative is positive, so 4 is greater than 0. That would be true, right? That would be true. So it's true. So then this interval is part of our solution set, right? Everything from negative infinity till we get to negative 1. Okay, let's test in between negative 1 and 2. Let's try 0. If we test 0, same, plug it back into those factored to the factored inequality, and that gives us 0 minus 2 times 0 plus 1 greater than 0. This would give us -2 times +1, -2 greater than 0. That's false, right? That's a false statement. So that means this entire region does not get counted as part of a solution. And then we test our last interval. We'll plug in 3. So let's test 3. That's 3 minus 2 times 3 plus 1 greater than 0. 3 minus 2 is 1, and 4 plus 1, 3 plus 1 is 4. So 1 times 4, that's 4 greater than 0. That means that this is a true statement. So therefore, this interval from 2 all the way to positive infinity would be part of our solution set as well. So now my solution, right, has to be an interval notation. So I would say that it goes from negative infinity all the way till we get to -1, but do not include -1. So we use parentheses. We have a gap, but then another interval. So I need a union. And then we start at 2, do not include 2, right? Open circle, till you get to positive infinity. So my solution is here, right? This is my solution. Solution set. Okay, there it is. Any questions on this example? Okay, let's go ahead and take a look at the next example. Next example is going to require us to expand, right? So take a look at the left. It's x plus 3 squared. Let's expand it. That gives us x plus 3 times x plus 3 greater than or equal to. And on the right side, we can also distribute. So this gives us a 2x squared plus 14. All right, let's expand the left side first. X times x is x squared. X times 3 is 3x. 3 times x is 3x. 3 times 3 is 9. Greater than or equal to the 2x squared plus 14. All right, there's some like terms we can combine on the left side. So do that first. So that gives us x squared plus 6x plus 9 greater than or equal to 2x squared plus 14. Okay. What do you think is the most appropriate move to make? Should we move the terms from the right to the left or the terms from the left to the right? Ideally, I would love to have a leading coefficient that's not negative. So since I don't want to have a leading coefficient that's negative, I'm going to start by subtracting x squared from both sides. Subtracting 6x from both sides. And also subtracting 9 from both sides. This becomes a 0. My inequality stays the same. 2x squared minus x squared is just x squared. Here I can't combine the 14 with the 6x, right? Since there is nothing to combine negative 6x with, that would be minus 6x. And 14 minus 9 would be positive 5. All right, so now let's go ahead and factor what's on the, let's go ahead and factor what's on the right side. We need factors that would multiply to be positive 5, but add up to be negative 6. So that would be x minus 1 and x minus 5. That will then help us get our two boundary points. X minus 1 is equal to 0. X minus 5 is equal to 0. So we end up with these two boundary points, x equals 1 and x equals 5. So here's 1, here's 5. What kind of inequality, I'm sorry, the inequality that we have tells us to do or to draw what kind of circles on 1 and 5. Yeah, these have to be closed, right? They would have to be closed because we can include them in our solutions. All right, so now we just have to find some test points. To the left of 1, that could be 0. In between 1 and 5, that could be 2. And then after 5 could be 6. So now we're going to test them once again into the factored version. It's the easiest one to test into. So let's try it. So we have 0 is greater than or equal to 0 minus 1 times 0 minus 5. 0 would be greater than or equal to negative 1 times a negative 5. So 0 greater than or equal to 5. Is that true or false? That's a false, right? 0 is not greater than 5. This is false. So this interval to the left of 1 does not get shaded. Okay, now we try the next value. 0 greater than or equal to 2 minus 1 times 2 minus 5. 0 is greater than or equal to 1 times negative 3. So 0 greater than or equal to negative 3. That one is true, right? 0 is greater than or equal to negative 3. We get a true, so we know that this interval will be shaded. And then we test the last one just in case. 0 greater than or equal to 6 minus 1 times 6 minus 5. So 0 is greater than or equal to 5 times 1. 0 greater than or equal to 5. That's a false, right? So that's another false. Therefore, the only interval, the solution interval that we have is the one just between 1 and 5. And we can include 5 and 1 because we have those closed circles there. So then this is what we have as our solution. Any questions on number 2 or on our second example so far? All right, let's go ahead and move on to the next example. So if you have the printout, this would be great, right? You can draw on it, you can highlight it. If you don't have the printout, that's okay. You can also kind of wait till I post these notes a little later, and then you can copy these onto your notes so you have them in front of you. These are the exact same equations. Okay, we have a question. Is our goal to make one side of the equal to 0 and later factor? Yes, that is our goal. That is our goal. Get everything onto one side, factor. When you factor, the reason why you factor is to help you find those critical points. Once you factor, you can then split it into two equations for the zero product using zero product property, right? And that tells you where the boundaries between the intervals are. Right? So typically, yeah, that's the approach. Get everything onto one side, factor, solve for the boundary points, and then test each boundary. So I'm going to go ahead and write down the expression down here again. It's the same one. It's just that these are the graphs. So we have x squared is greater than x plus 2. Okay. So taking a look at this, I have my quadratic x squared. That's one function, right? It's clear which one it is. It's the only parabola that I have. So x squared is represented by the parabola. And x plus 2, that's just a linear function, right? It's a linear function with a slope of 1, and it has a y-intercept at 2. Okay, so these are the two functions that we're working with. So let's see what the question is. It's basically asking, where is x squared greater than x plus 2, right? Where is the parabola greater than the line? So what we would do first is we're going to find those points of intersection because that is what creates the boundaries. And there's another one here. So you see, now I have these three intervals. I have interval A, interval B, and interval C. Where do you see that the parabola is above, greater than the line? Like, what intervals do you see a parabola being above the line, being greater than the line? Okay. Interval A and C, right? So since it's open circle, once again, because of the inequality, it's open circle at 1, I'm sorry, -1, and then open circle at 2. And we said, hey, that the parabola is greater than the line in these two sections, right? Section A and section C. Then this is where we can say, all right, then on the interval, right, everything to the left of -1, the parabola is greater than the line, and everything to the right of +2, the parabola is also greater than the line. So then the interval, the solution interval becomes the same. It's from -infinity to -1, union with 2 to infinity, right? It's the same interval set that we got when we solved algebraically, right? Okay, any questions on number 3? Questions, all right. And let's take a look at the last one then, which is the x plus 3 squared greater than or equal to 2 times x squared. Let me write it as the distributed version, 2x squared plus 14. All right. So now the tricky part with this problem is like identifying which one is which, because we have two parabolas. You see how we have x plus 3 squared? When we expanded that, that's a parabola, that's a quadratic. And then the 2x squared plus 14, that's also a quadratic. So part of the problem is just identifying which one is which. Let's start with this one. The 2x squared plus 14. All right, this is a parabola that plus 14 typically indicates where it crosses the y-axis. Okay. So the 14, we can treat that as like, that's my y-intercept. Okay, because if x was 0, that means if I plug in 0 for x, that means what's my y value? My y value would be 14. So these look like they go by 5s. 10, 15, 20. So this one, since it crosses right here, right below 15, it's pretty safe to say that that quadratic, that parabola, is going to be represented by this one in green. Right? That would be my 2x squared plus 14. Which means that then the other parabola, the x plus 3 squared, that's going to be the other line that we see. Right? You can see that this one, x plus 3 squared, that means it has a vertex of negative 3 comma 0. Because it has no k value, but it does have a plus 3 inside the parentheses, so it's opposite keep. So it does have, looks like it crosses the y-axis there at negative 3. Okay, so that tells me this is my blue one. All right, so once again, we look at the points of intersection. Points of intersection happen here. And they happen here. So we care about, well, what's that x value? So if this is 2.5, then that means these probably go by 0.5. So 0.5, 1, 1.5, 2, 2.5. So when I draw this boundary, right, my number here would be 1. And then for this one, that looks like it would be 5. So now if I go back and I look at my inequality, right, what kind of circles would I draw at 1 and at 5? Yeah, we draw some closed circles. That's right. Yeah, we can include the value, right? It can be equal to 1 and equal to 5. So now where do you see the blue quadratic greater than or equal to the green quadratic? Interval A, interval B, or interval C? Where do you see the blue greater than or equal to the green? Where do you see the blue is above? Yeah, interval B, right? Interval B, which is right here in between the 1 and the 5. So that tells us our solution interval is going to be bracket 1, comma 5 bracket. And this represents our solution set.